Welcome to my YouTube channel Easy Mathematics. From this lecture onwards, we are going to start the advanced graph theory. And the first topic of this advanced graph theory is tree. Tree is a special kind of graph, which is the most powerful graph of the advanced data structure, and it often pops up in even more advanced subjects such as artificial intelligence, compiler designing, and circuit theory. The tree can be manipulated for hierarchical data, make informations easy to search, manipulate short lists of data as a workflow of compositing digital images for visual effects and router algorithms. In fact, there are vast application area of this tree. So what is tree? A tree is a simple connected graph. A tree is a simple connected graph without any circuit. So, for example, let us consider this one as a graph. Only one vertex is there. So, no circuit is there. It is a simple graph and it is definitely connected. If we think of a graph with two vertices only and it is connected by one edge. So, no parallel edge, no self loop is there. So, it is a simple graph and it is connected also, and it have definitely no circuit. Circuit means in between two vertices there should be a path, in fact two paths if the circuit is formed, but here only one path is there from the one vertex to another vertex. So this one also we can say as the tree. For another example, we can think of the vertex with graph with three vertices. Here also this one is a simple connected graph without any circuit, so it is also a tree. Again this one, here the total 5 vertices are given and no circuits are there, so it is also a tree. In fact, this one is again a graph without any circuit and it is a tree. There are few basic terminologies which we use in case of the tree. So tree in general, in our environment we find out the trees. So these trees we have the root, the branches, the leaves and all. Here in the graph theory also we can find out the similarity with that tree even. But the basic difference is our graph theoretic tree is just the reverse of the natural tree. That means root lies in the top and the leaves lies in the bottom of the tree. So at first we come to know about few terminologies. So first one is the root. So what is root? The topmost node in a graph is a tree. The topmost node in a tree is called the root. So here this one we can say as the root, this one we can say as the root, here this one we can say as the root, and here this one we can say as the root. Next it is the pendant node. So a node that has a child node is called the parent node. So now look, here any node which have the child means if from one node any edge is going out, then these are termed as the child. So this one is the parent node for these two edges. Similarly, this one is the parent node for these two edges. Again, this one is the parent node for these two edges, and likewise. Next is the siblings. Siblings are what? Nodes with the same parents. That means we can say these two nodes are the siblings because both of these two nodes have the same parent. Again, these two we can say as the sibling because it's both for them have the parent, this one. Next it is the internal nodes. Internal nodes are that nodes which lies inside the graph. So the node with at least one child is called the internal node. That means if any node is given and it have any child node, then we can say the node is the internal node. In fact, except the root and except the lower nodes, whatever the nodes lies in the graph, these are called the internal nodes. So for this graph, this one, this one, this one, then this one and this one, these are the internal nodes. Next it is the leaves. So leaves are what? That is the nodes with no children. So these are the end nodes. So here this one we can say leaf, this one, this all are the leaves. In fact, we can say the vertex with degree 1 is the leaves. So look, any vertex in a tree with degree 1 are termed as the leaf. These are also called the pendant node also. Next, it is the height of a node. So what do you mean by the height of a node? That is the length of the longest downward path between the node and the leaf. In this graph, we can say the highest node is this one, because 1, 2, 3, that is the longest path in between these two nodes. Next, it is the label. Label is one of the most important thing in the tree structure of graph theory. So what do you mean by the label? So label is the number of edges between the node and the root. So here in the graph we can say the first node, this one is at the level 0. Then its second step, these nodes are at the level 1. Here the level 0, these are in level 1, these are in level 2. Now here this one is level 0, this one level 1, this 4 are in level 2, then this one in level 4, and these two are in level 5. And one more thing, that is called the forest. So a set of n greater than equals to 1 disjoint trees are called the forest. So if we consider all those graphs together, then this together may create the forest. So these are the few terminologies regarding the tree. Next, it is some important theorems on the tree. So the first theorem is, in a graph G, there is one and only one path between every pair of vertices. Then G is a tree. So how to prove this one? What is the theorem? In a graph G, there is one and only one path between every pair of vertices. Then G is a tree. So how to prove this one? If there is a path between every pair of vertices, then G is connected. That is very obvious. Now we have to prove that G has no circuit. If we can prove that G has no circuit, then we can prove that in between any two vertices there are not more than one path. If we can prove that in between any two vertices there is exactly one path, then we have done. So a circuit in a graph implies that there is at least one pair of vertices, say U and V, such that there are two distinct paths between U and V. Since G has one and only one path between every pair of vertices, therefore G can have no cycles. And when G have no cycles, then we can say the graph is a tree, and hence the theorem. Next theorem is a tree with n number of vertices has n minus 1 number of edges. This one is the most important theorem in our tree. So what is the theorem? In a tree with n number of vertices has n minus 1 number of edges. So how to prove this one? Let a graph is given which is T. So this one is suppose the given graph. Now the theorem can be proved by method of mathematical induction depending upon n, the number of vertices in T. Let T have containing n number of vertices, and this one is a tree. So E is one of the edge of this tree. So this edge connects the vertex V2 and V5. Now if we just remove this edge from this tree, then what happens? This tree becomes disconnected. If we remove this one, then this tree becomes disconnected. So now we know that every disconnected graph consists of two or more connected graphs called the components. So if we remove this edge, then what happens? This one is one part of the graph and this one is the another part of the graph. So the graph becomes the two parts, and we can say each of these two are the two components of the graph. So after removal of E, we will find out the two components of the graph. So now the graph T minus E, that means this graph after removal of E, the newly graph is T minus E, which is this one. So this one has exactly two components. Say the first component is T1 and the second component is T2. So pictorially we can say this one is our T1 and this one is T2. Now let T1 contains N1 number of vertices and T2 contains N2 number of vertices. Then the total number of vertex should be N1 plus N2. Now if T1 contains a circuit, then T would have a circuit. It is very obvious. If T1 contains a circuit, then T definitely contains a circuit, which is not possible. So T1 is a tree. Similarly, T2 is also a tree. So by our hypothesis that T1 has N1 minus 1 and T2 has N2 minus 1 number of edges. Thus, T minus E consists of N1 minus 1 plus N2 minus 1 is equals to N1 plus N2 minus 2, that is N minus 2 number of edges totally. So T minus E, that graph contains the total number of edge, which is N minus 2. Now hence the graph T has total N minus 1 edge because one edge we have removed from T to get the T minus E graph. So N minus 2 is the total number of edge for T minus E. With that, if we add this one removed edge, then we will find out the total number of edge is N minus 1. And hence the theorem. Here you should note that the converse of this theorem is also true. That is, the connected graph with N number of vertices and N minus 1 number of edges is a tree always. So one more theorem for the tree structure is that a graph is a tree if and only if it is minimally connected. So minimally connected, what does it mean, the minimally connected? A connected graph is said to be minimally connected if removal of any one edge from it disconnects the graph. That means if we remove one edge and at least any one edge from the given graph, and after removal of that edge, the graph becomes the disconnected, then we can say the given graph is a minimally connected graph. And for a minimally connected graph, that is always has to be a tree. Just because, just look at this one is the example of a tree. Among these edges, if you remove any one of the edge, then we will find out the graph becomes disconnected. Here we remove this one, so it becomes in two parts. Instead of this one, if we remove this one, then this one is the one part and this vertex remains in the second part. So any one edge you may remove from this graph, you will find out that the graph becomes disconnected. So a minimally connected graph is also termed as a tree. Now one problem for the tree, let us do here. So what is the problem? The problem is a tree has two vertices of degree 2, one vertex of degree 3 and 3 vertex of degree 4. Now how many vertices of degree 1 does it have? So how to solve this one? So what is our requirement? Our requirement is how many vertices of degree 1 does the tree have? So initially let x be the number of vertices with degree 1. So now the total number of vertices in the given tree is n, which is 2 here because it is given that 2 vertices of degree 2, 1 vertex of degree 3 and 3 vertex of degree 4 and x vertex of degree 1. So this is the total number of vertices in the given graph, that is 6 plus x. So now, hence the number of edges should be, we know, n minus 1. Hence the total number of edges is 6 plus x minus of 1, that is 5 plus x. Now the total degree of the given graph. So in the given graph, it is in the problem given that 2 vertices with degree 2, 1 vertex with degree 3 and 3 vertex with degree 4, and according to our hypothesis, x number of vertices with degree 1. So if we do this calculation, then it will leads us the 19 plus x, that is the total degree count for the given graph T. Now by the handshaking theorem, the total number of edges in a graph we know that is the total degree divided by 2. So now if we equate these two equations, that is equation number 1 and this is equation number 2, both are same. So if we equating these two equations, then we will find out 5 plus x is equals to 19 plus x by 2. If we simplify, then we will find out x is equals to 9. Here, if this one is the graph, so here we can say that total number of 9 vertices are there with degree 1. So for real example, if we consider this one as a tree, then here the vertices with degree 1 is 1, 2, 3, 4, 5, 6, 7, 8 and 9. In fact, you may draw any tree and accordingly you just calculate. You will find out this number will be according to this theorem. This lecture is about the binary tree. So, tree we come to know. Now it is the binary tree. So, what is binary tree? Before come to know about that, we should know the rooted tree. So, what is rooted tree? A tree in which one vertex called the root is distinguished from all the other vertices. This one is called the rooted tree. That means, for instance, if these are the trees, then the vertex which we termed as the root, so these are, if exist, then we can say that this is the rooted tree. Now it is the binary tree. A rooted tree in which there is exactly one vertex of degree 2, which is the root, and each of the remaining vertex is of degree 1 or 3 is called the binary tree. So what does it mean? The binary tree means a tree which contains exactly one vertex as a root with degree 2, and the remaining all vertices are of degree either 1 or the degree 3. So if this one is a tree, then just look here, this vertex having degree 2, and no such vertex exists in this tree which having degree 2. In fact, this vertex having degree 3, this vertex having degree 3, this vertex having degree 1, this vertex having degree 3, this one degree 1, this one degree 3. This one is of degree 1, this is degree 1, this is degree 1, and this is also of degree 1. So in this graph, we will find out that exactly one vertex which is of degree 2 and the remaining vertices are of either degree 1 or degree 3. Then such type of trees are called the binary tree. So here in the binary tree, the root should be assigned the label 0, and just in the next step, this is assigned to be the label 1. Then these 4 vertices are in label 2 and these are in the label 3. So for any binary tree, we should come to know that the number of vertices is always odd. So this is a conclusion from the binary tree, that the number of vertices is always odd. Just count here the number of vertices. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. Here total 11 number of vertices are there and it is an odd number. That is because we know that total degree count of the vertices for any graph is always an even number. Now for the binary tree, only one vertex is there whose degree is 2, which is an even number, and remaining all vertices are of degree either 3 or 1. These are the odd numbers. So now if we add the odd numbers and ultimately if our requirement is an even number, then the total number of odd numbers should be even, so that To get the total degree count even, it is obvious that the total number of vertices in a binary tree always be an odd number. What is the next observation? The next observation is, if the number of vertices of degree 1 is m, then the number of vertices of degree 3 is n minus m minus 1, where n is all vertices. What is the conclusion? That the number of vertices of degree 1 is m. Then the number of vertices of degree 3 is this one, where n is all the vertices. How to get this one? For this proof, we are coming in the next theorem. And one more conclusion is for binary tree is that the number of rooted binary tree with n number of vertices is 1 upon n plus 1 into 2n cn. So how we will get this? So for that we will find out this theorem on binary tree. So the first theorem is what? The number of vertices in a binary tree is always odd. So how to prove that? So proving that one for, let a binary tree has n number of vertices. Now since a binary tree has one vertex of degree 2 and other vertices of degree 1 or 3, so there are n minus 1 number of odd degree vertices. Since we know the number of odd degree vertices in a graph is always even in number, therefore n minus 1 is an even integer, and it is very obvious then n is an odd integer, and hence the total number of vertices in a binary tree is odd. The next theorem is what? That is, prove that the number of pendant vertices in a binary tree is n plus 1 by 2, where n is the number of vertices. So pendant vertex means the vertices of degree 1. So let x be the number of pendant vertices in a binary tree, where x is the number which having the degree 1. So now T has only one vertex of degree 2 and each of the other is of degree 3. It is very obvious because we know that in a binary tree one vertex of degree 2 and the remaining vertices are of degree 3 or 1. X is the number where the vertices having degree 1. So the x and 1, x plus 1 number of vertices are there with degree 1 and 2, and then the remaining vertices are of degree 3. So the sum of the degrees of all vertices of T is x into 1 plus 1 into 2, and the remaining means n is the total number of vertices, so n minus x plus 1. So it is n minus x minus 1 into 3, that is of degree 3. So if we simplify, we will find out 3n minus 2x minus 1. So now we know that the sum of all degrees is equals to the number of 2 into the number of edges. So therefore the number of edges in T is n minus 1, that we know. For any tree the total number of edges are n minus 1. So accordingly we can write 3n minus 2x minus 1 means this one is equals to 2 into n minus 1 from the handshaking theorem. So which will implies, if we simplify, it gives us x is equals to n plus 1 by 2, which is the proof. So now one more theorem. So that is the theorem, the number of internal vertices in a binary tree is 1 less than the number of pendant vertices. So according to the theorem, if you have total n x number of vertices as the pendant vertices, then the total number of internal vertices are x minus 1. So how to prove that? So let the binary tree contains x plus y vertices, where x is equals to the number of pendant vertices and y is the number of internal. N is equals to x plus y, that is the total number of vertices. So we know the number of pendant vertices in a binary tree is n plus 1 by 2. Therefore x should be n plus 1 by 2, which will implies that x is equals to x plus y plus 1 by 2, because we know n is equals to x plus y. So if we simplify, then we will find out from here y is equals to x minus 1, which is our requirement, hence the theorem. One more thing which is very important for the binary tree is that the maximum number of vertices possible in a k-label binary tree is 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus in this way 2 to the power k, which is greater or equals to n. So if this one is the binary tree, then according to the theorem, it is the maximum number of vertices possible in the k-label. So if we consider the label is 0, then the maximum number of vertices should be here 2 to the power 0, that is 1, which should be greater than equals to n. So n is 1. Next, at the label 1, the maximum number of vertices should be 2 to the power 0 plus 2 to the power 1. That is 1 plus 2, that is total 3, which we can write greater than equals to n. Here n is 3. If we consider the label 2, then just look here, when k is equals to 0, then 2 to the power 0 only. When k is equals to 1, then this is the formula. When k is equals to 2, then we will get this one is 7. And when k is equals to 3, then we will get this one, and so on. So actually, this theorem leads to that the maximum number of vertices possible. So if we consider here the label 4, so here look, the maximum number of vertices, maybe it is 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 plus 2 to the power 4. That sum definitely not gives you the total sum of here, because few vertices are missing here, because it may be possible to draw the leaves from these vertices also, but we have not drawn. So the maximum number of vertices are for this label is, it is 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 plus 2 to the power 4, which should be greater equals to n. So maybe the number of vertices in any label is less than that value, but not more than that. So this is the theorems for the binary tree, and I hope you understand. In this video lecture, we come to know about some terminologies regarding the tree and the other graphs also. These terminologies are distance, eccentricity, center, radius, and diameter. So we are going to disclose one by one. Initially, it is the distance. So in a connected graph G, the distance between any two vertices is valid for any connected graph. Not necessarily it should be a tree. In a graph that is not a tree, there definitely be more than one path between any two vertices, may or may not be. So we have to find out the shortest path between those two vertices. So in proper definition, we should say in a connected graph G, the distance d vi vj, d is the notation for the distance, and vi vj denotes the any vertices, any two vertices. So between two of its vertices v1, vi and vj is the length of the shortest path between them. So what do you mean by the distance? That is, in a connected graph G, the distance d between two of its vertices vi and vj is the length of the shortest path between them. So for example, if we consider this graph and let us want to find out the distance between v1 and v3. So if we want to find out the distance between these two, then how many paths or how many possible paths are there to reach from v1 to v2, that we should analyze. So here at first we can move from v1 to v2, then v2 to v3, then that is the one of the possible path. So we should write it as e1, e2, because these are the two edges which are included to move from v1 to v3. So e1, e2, and its distance is 2. So this is the one of the path in between v1 and v3. Now e6, e8. So e6, e8 means v1 to v6, then v6 to v3. That is one another path to reach from v1 to v3. Now it is E6, E5, E11. So E6, E5, E11 means this is E6, then E5, then E11. This is one more possible path. One more we have E1, E7, E8. So E1 is this one, E7 is this one, then E8 is this one. So look, these are the all different paths to move from V1 to V3. Among all these possible paths, we should find out which path covers the minimum number of edge. Or better to say, what is the shortest path between V1 and V3. That particular path is the shortest path, and the distance, that means the value, how many edges are included there, that value is the distance between these two vertices. So here for V1 and V3, if we collect all possible paths, not necessarily only these four, but more than that also be possible. So among all these, we will find out that the path with distance 2 is the shortest one. So that we can say the distance between V1 and V2 is 2. Similarly, we can find out the distance in between any two vertices. So, if it is a tree, so in a tree, since there is exactly one path between any two vertices, then the determination of distance is much easier. If any graph is given, then here in between any two vertices, there may be possible that more than one path exists. But if it is a tree, then it is very obvious that in a tree, there exists exactly one path in between any two vertices. So for example, suppose this one is a tree. So in this tree, in between any two vertices, we have exactly one path. Let us consider the vertex V1. So V1 to V2, there is the distance 1. Then V1 to V3, the distance is 1. Then V1 to V4, the distance is 2. Then V1 to V5, the distance is again 2 because 1 and 2 edges are included. V1 to V6, here the distance is 3 because 3 edges are included here, and V1 to V7, it is 3 again because 1, 2, 3 number of edges are included. So we will find out the distances of V1 from all the other vertices. So the distance of any two vertices is given with respect to V1 here. Similarly, with respect to V2 also, we can find out the distance for all the other vertices. So in this way, we can find out the distance for the tree as well as the distance for the any graph what we have chosen for. And definitely in the distance, we definitely not cover the self loop and the parallel edges. Now one next terminology is the eccentricity. Eccentricity is denoted by EV. V stands for the vertex for what we are going to find out the eccentricity. So what is eccentricity? The eccentricity EV of a vertex V in a graph G is the distance from V to the vertex furthest from V in G. So that mathematically we can write eccentricity of V is the maximum of distance from V to Vi. So what does it mean? That from the vertex V to any other vertices present in the graph, we should find out the distances. That means from V to all other vertices, we find out the distances. After finding out all those distances, we search that which distance from V is the maximum. That maximum value is the eccentricity for the vertex V. So for example, suppose this one is a given graph. So here total 6 vertices are given: V1, V2, V3, V4, V5 and V6. So now V1 from V1 to V2, the distance between V1, V2 is 1. Then V1, V3 it is 2. V1, V4 it is 3. V1, V5 it is 4. And V1 to V6 it is 2. So from V1 we will find out the distances, all possible distances for other vertices. Now among all those distances, the maximum distance is, we will find out it is 4. So we can say for the vertex V1 the eccentricity value is 4. So look, eccentricity for V1 is 4. Likewise, we find out the distances from V2. So V2 to V1 already we know, that is V1, V2 and V2, V1 the same thing. Now V2 to V3 it is 1, V2 to V4 2, V2 to V5 it is 3 and V2 to V6 it is again 1. So we will find out all possible distances. So for V2 to all these 5 distances are there. Among all these, this one is the highest one or the maximum distance. So the eccentricity value for V2 is 3. Likewise, we can find out the eccentricity value for all other vertices. At first, we just calculate the distances of the other vertices with all the respective vertices and find out which one is the maximum. And accordingly, we can find out the eccentricity values for this particular graph of each vertices is eccentricity for V1 is 4, eccentricity of V2 is 3, eccentricity of V3 is 2, and for V4 the eccentricity is 3, V5 the eccentricity is 4, and for V6 it is again 4. So in this way we can calculate the eccentricity for any vertex in a graph. So next it is the center of the graph. So a vertex with minimum eccentricity in a graph G is called a center of G. So what does it mean? A vertex with minimum eccentricity in a graph G is called the center of G. So if we consider the same graph, here the eccentricity value for all given 6 vertices are this all. Among all these eccentricity values, the minimum eccentricity value is for V3, that is 2. So among all those eccentricity values, which vertex have the minimum eccentricity value, that particular vertex is called the center of the given graph. So here the center is V3. So how to calculate the center? Mathematically we can write the center of a graph G is the minimum of the eccentricity. For the given example it is V3. Let us consider one more example. So this one is a graph. Here we should find out the eccentricity values for all the vertices. So here the eccentricity for V1 it should be 3 because the longest path from V1 is 3. So eccentricity for V2 is also 3, for V3 it is 2, V4 it is 2, V5 it is 3 and for V6 it is 3. So we will find out all the eccentricity values for the given vertices. Now the minimum eccentricity value is 2, but it occurs for 2 vertices. It occurs for 2 vertices. So that we can say the given graph has 2 centers and these 2 centers are V2 and V3 both. So accordingly we have few observations. So what are those observations? So first of all, every tree has either 1 or 2 centers. Remember, in a tree you may find out either 1 center or 2 centers. Not more than 2 centers are possible for any tree. If your graph is a tree, then not more than 2 centers are possible. A general graph may have more centers. If your general graph is given, then you may find out 1, 2, 3, 4. It depends upon the calculation that how many centers are there. If the graph is a cycle, so like this one is a cycle. In this graph, all the vertices are the centers. Not only that, if your graph is a complete graph, then in a complete graph also all the given vertices are the centers. Next, in a tree, if 2 centers exist, then they are adjacent to each other. It is again very obvious that if in a tree 2 centers exist, then these 2 centers has to be lies as they are adjacent. Otherwise, you will find out only 1 center. Now, one more definition, that is the radius. What do you mean by the radius? The eccentricity value of a center in a tree is defined as the radius of the tree. So, we know what is the eccentricity value of the center. At first, a graph is given. From there, we should find out the eccentricity. After getting the eccentricity, we should find out the center. Now, center is a specific vertex. That vertex for you know the eccentricity value. that particular eccentricity value is called the radius of the center. So the eccentricity value of a center in a graph, in a tree, is defined as the radius of the tree. Next, it is the diameter. So what do you mean by the diameter? So the diameter of a tree T is defined as the length of the longest path in T. So what do you mean by the diameter? Let this one is the given graph, and we find out the eccentricity value for all these 7 vertices. After getting these eccentricity values, the minimum eccentricity for V3 is given, so that V3 is the center and the radius is 2. And the diameter for, we should find out the maximum eccentricity value. The maximum eccentricity value is 4, so that we can say the diameter is 4 for the given graph. So these are the few terminologies which are related to any graph as well as the tree also, but these are very important, so that we discuss here. The next lecture is for the spanning tree. That in this video lecture we are going to discuss the most important topic of tree, that is the spanning tree. But before starting the spanning tree, we should come to know about the subgraph of a graph. So a graph H is said to be a subgraph of a graph G if all the vertices and all the edges of H are in G, and each edge of H has the same end vertices in H as in G. So what is the subgraph? For example, we should discuss that. Let this one is a given graph. This graph have total 6 vertices, V1, V2, V3, V4, V5 and V6. And here total 10 number of edges are given. E1, E2, E3, E4, E5, E6, E7, E8, E9 and E10. Now this one is a given graph G. If we consider a graph having only the vertices V1, V2, V3 and V6 and the edges E1, E2, E10, E9, that is this graph, then this one we can say is the subgraph of the graph G. Again, we can consider another graph which consists of the vertices V1, V4, V3, V5 and these edges, so that we will get this graph. This one we can say one more subgraph of the given graph G. In fact, from the given graph, if we consider any part of the graph, then that one is the subgraph of the given graph. Just the concept of subset which we know in the set theory, the same concept we can apply here. Graph is given. We may consider any 1, 2 or 3 vertices or all the vertices even, and the edges, few edges from here. But definitely just remember that if E1 you have considered as in the subgraph, then its connectivity should be V1, V2 in the subgraph also. That adjacency relation will not change in the subgraph. So the graph is given, it's any part if you consider as the smaller graph, then this one is called the subgraph of the given graph. Here we have given 2 examples, H1 and H2 as the subgraph of it. Now from here we can say that every graph is its own subgraph. If we consider the entire graph itself, then it is the subgraph of it. That we know from the set theory also. A single vertex in a graph G is a subgraph of G. Obviously, if we consider V1 only as the subgraph, then it is a subgraph definitely. Now it is a single edge in G together with its end vertices is also a subgraph. If we consider only the vertex V2, V3 with E2, then this one we can say is a subgraph. Now suppose H is the subgraph of G and K is one another graph which is the subgraph of H. Then we can say K is the subgraph of G. In this context, we can define two types of subgraph. One is called the edge disjoint subgraph and another one is the vertex disjoint subgraph. So edge disjoint subgraph is what? If H1 and H2 are two subgraphs, but H1 and H2 have no edge in common, then it is called the edge disjoint subgraph. For example, if we consider this one as H1 and H2, these two are the subgraph from the given graph G. But look, H1 and H2 have no edges common. Then H1 and H2 are called the edge disjoint subgraph. Similarly, vertex disjoint subgraph is what? Here H1 and H2 are the two subgraphs, but H1 and H2 have no vertex in common. That means no vertices are the same in case of the vertex disjoint subgraph. Look at these two graphs. Here V1 is common in both, so that we can't say that these are the vertex disjoint subgraph. In vertex disjoint subgraph, no vertices in H1, H2 are common, and very obvious then edges are also not common over here. Now, so far we have discussed the tree and its properties when it occurs as the graph by itself. Till that we come to know about the just simple tree, then binary tree and all. Everywhere we directly draw the tree. So we consider the itself a tree as a graph. Now we consider a graph, any graph it may be, and tree is the subgraph of the given graph G. So if a graph G has E number of edges, then the total number of possible subgraphs of G are 2 to the power E. So from the given graph G, we can find out so many subgraphs. So how many all possible subgraphs can be possible? For that, the formula is 2 to the power E. So let me explain that one, how it is 2 to the power E. If G has 3 edges, suppose G is a given graph with 3 edges, then all possible subgraphs are, it is 2 to the power 3 according to this one. So that we will find out as 3C0, 3C1, 3C2, 3C3. So this is actually the binomial theorem which we know. So what happens? Suppose this one is the given graph with 3 edges. So now from these 3 edges, out of 3 edges, if we will not consider a single edge, then here out of 3 no edges are chosen. Then it is out of 3 edges only any one edge may be chosen. How many ways? Out of 3 edges, how many ways we can choose? 2 edges. And out of 3 edges, how many ways we can choose? All 3 edges. If we add all these 3, then we can find out that how many possible ways to construct the subgraph. And obviously, if 3C0 is 1, 3C1 is 3, 3C2 is 3, and 3C3 is again 1. And its summation is 8. And hence the total count is 2 to the power 3. Similarly, here the given examples, that means here the 3 edge with a graph G is given, and its subgraphs are this 8. First one, second one, third one, fourth one, fifth one, sixth one, seventh one, and eighth one. Similarly, if we consider a graph with 4 edges, then all possible subgraphs are obviously 4C0, 4C1, 4C2, 4C3, 4C4, and their summation. So it should be 1 plus 4 plus 6 plus 4 plus 1, that is 16, which is 2 to the power of 4. So in this way we can find out all possible ways, all possible number of subgraphs in a given graph which can be formed. So now it is very obvious that in the given graph form, we have the different subgraphs, and those subgraphs from some are the trees. Just look at this one. Here from this one we can say a tree, this one is a tree, this one is a tree, this one. In fact, except this one and this one, the remaining all graphs are the tree. So some of the subgraphs will be tree among all those trees, among all the given subgraphs. And among all those trees, some trees are termed as the spanning tree. So what is the spanning tree that we are going to discuss now? A tree T is said to be a spanning tree of a connected graph G if T is a subgraph of G and T contains all the vertices of G. Here you just remember one thing. The spanning tree is the spatial tree which consists of all the vertices from the given graph G. For example, if we consider this one is the graph G, here total 8 number of vertices are given. So total 8 number of vertices with, we have to draw a tree which consists of all those vertices. Then it is very obvious that total number of edges should be n minus 1, that is 7 here. So we can say that this one is the spanning tree from the given graph. It is mandatory that all the vertices should be included in this graph, in this tree. So we can say about the spanning tree that it is a skeleton of G. It is the skeleton of G, a rough structure of the given graph G. It is termed as maximal tree subgraph of G. This spanning tree is termed as the maximal T subgraph because just look, if we consider the largest tree from this graph, then it should be the spanning tree. If we delete any one edge from this one, then definitely it remains a tree and it should be a subgraph even. But it is no more a spanning tree because deletion of any edge will remove the corresponding one vertex, which will not include all the vertices of the given graph G, which is mandatory for the spanning tree. Hence, it is no longer be a spanning tree. So, for the spanning tree, all the vertices should be included. All the vertices should be included means it is the maximal tree subgraph of G. Now, there may be more than one spanning tree in G. In G, there should be more than one spanning tree. It is again very obvious. Instead of these edges, we may choose some other edges also. For example, suppose instead of this edge, if we include this one, instead of this edge, if we include this one, then also it remains the spanning tree and it will concise all the requirements. Now, the edges included in a spanning tree are called the branch of the tree. It is again very important. Whatever the edges we include in the spanning tree, these edges are called the branch. Edges which are not included in the spanning tree, these edges, that means here these color edges which are not included in the spanning tree is called the chord of the tree. And then it is very obvious that the total number of branches and the chords makes the total number of edges from the given graph. So an edge which is not included in the spanning tree T of G is called the chord. Now every connected graph has at least one spanning tree. If a graph is given which is connected, then it definitely have one spanning tree. For a graph, there are more than one spanning tree. That is very obvious. So, but if the graph is connected, at least one spanning tree we have to find out. Now, the last thing is any spanning tree of a connected graph G with n number of vertices and e number of edges has n minus 1 number of branches and e minus n plus 1 number of chords, which I told you previously, that the total number of edges in the spanning tree should be n minus 1 and the total number of chords, total number of branches are n minus 1 and total number of chords are e minus n minus 1. So, if we add the total number of branches and the chords, then we will find out the total number of edges for the given graph. Next, it is the weighted graph. So, now what is the weighted graph? A graph G is said to be a weighted graph if there is a real number associated with each edge of G. So, for example, if this one we consider as a graph, in this graph all the edges have a specific weights. So, this one is called the weighted graph. Now, from here we should come to know about the minimal spanning tree. So, if G is a weighted graph, then the weight of a spanning tree T of G is defined as the sum of the weights of all branches in T. In general, different spanning trees of G will be of different weights. A spanning tree with the smallest weight in a weighted graph G is called a shortest spanning tree or minimal spanning tree. So, what is the minimal spanning tree? Minimal spanning tree means from this given graph, we should find out the spanning tree. It may be any one, but for all those spanning trees, we should find out the weight of the spanning tree. Weight, how to find it out? We should add, here this one is the spanning tree, one of the spanning tree. Then these weights are given for the corresponding edges. If we add all those weights, then we will get the total weight of the spanning tree. In this way, whatever be the different spanning trees are possible to construct from this given graph, we find out the weight for all individual spanning trees. So among all those spanning trees, which spanning tree have the minimum number of weight, have the minimum weight value, then this one is called the minimal spanning tree. It have a immense use. So for one application of the spanning tree, we can say that suppose we are connected to n number of cities, and these n cities are termed as the n number of vertices V1, V2, V3 and Vn. So through a network of roads, these cities are connected through a network of roads. Now suppose some costs are there to build the direct road between any two cities. For the two different cities, there is a different value for the costing is given. If we consider this graph only, and if we suppose that these vertices are the cities and these are the corresponding construction cost between connection of these two cities by roads, then we can say that if in between any two cities, suppose this one is say Vi and this one is say Vg, then in this given pair of cities where the roads can be built, then how to find out the way by which we can do this cost minimum? Our requirement is to connect all those cities by the specific road connectivity with the minimum cost. So for that, we can take use of this minimal spanning tree. We should find out the minimal spanning tree to get this cost minimum. So in this way, we can find out the spanning tree, and for the different graphs, there are so many spanning trees can be formed, and if it is the weighted graph, trees are specific. But how to find out the minimal spanning tree from the given graph, that is a big question, because suppose from a graph, if there are 50 different spanning trees can be possible. So for the 50 spanning trees, you should find out the different weights for each spanning tree, and then among all those, which one is the minimum that you have to identify. But that is a very hectic job. So for that, we have few algorithms by which directly we can find out the minimal spanning tree. Those algorithms we discuss in our forthcoming lectures. Hello students, welcome to my YouTube channel Easy Mathematics. In our last lecture, we come to know about the spanning tree, and we also come to know that for any graph there may be more than one spanning trees. But how to get all those spanning trees, this is a difficult job if your given graph is a complex graph. So to get the spanning tree with a systematic manner, there are few algorithms. So among those algorithms, we are going to know the BFS, that is the breadth first search algorithm. So in a given connected graph G, there are a large number of spanning trees. To get a spanning tree from a given graph G, we discuss one algorithm which is known as BFS or breadth first search algorithm. Now, what are the steps? So the following are the steps to get the spanning tree from any connected graph G. So what should be the steps? At first we come to know all that. After that, with an example, we find out this BFS algorithm. So the first step is what? It is the discard all the parallel edges and the self loops from the given graph. So any graph G may be given. The graph should be undirected and the connected graph G. Then from this graph, we should remove all the parallel edges and the self loops. That is the first step. And accordingly, we convert the given graph G to a simple connected graph. In the second step, we choose any vertex from the given graph. Any vertex. So that vertex chosen should be termed as the root of the spanning tree. And this vertex should be give the label, and that label name is the 0. So that is the 0th label, because we know in a tree the root should be at the 0 label. That we know from our previous video lectures. So the label of the root should be 0, that is assigned. And remember, root can be chosen as any vertex from the given graph. After that choice, add all edges incident to this vertex such that the addition of edges does not produce any cycle. Next, what to do? We should add all the edges which are incident to that vertex. That means whatever the vertex we have chosen as a root, with that vertex, whatever the adjacent vertices are there, we should choose all those vertices, and with them, whatever the edge connectivities we will find out, that we should connect in such a manner so that no cycle should be formed. Now, all those adjacent selected vertices should put the label 1. In the next step, what we will do? In the selected that adjacent vertices should put the label 1. Now, for each vertex at level 1 visited in order, add edges incident to this vertex and not produce any cycle. What we will do here? After in the label 1, we just go one after another the vertices, and for each vertex we should find out that any vertex is incidenting to that. That means from any vertex there is a edge connectivity or not. Just remember which vertices get the labeling value. We should leave those vertices, and which vertices are yet to give any labeling value, that vertices only we should consider in the second label. So we just choose in the first label each and every vertex one after another, and for each vertices whatever the edge connectivities we will find out, that is the incidenting edges we will find out, we choose all those edges and the corresponding vertices, and in the next label we put those vertices as the label 2. So after doing this one, we have one more step. So what we will do? So now continue the same procedure until all the vertices in the graph G have been added and labeled. So in this way we just continue, and we will do that until all the vertices are covered. After doing all this, we will find out a spanning tree. Since we have created a subgraph of G without any cycle containing all the vertices of G, that is the n number of vertices if the graph have, then we will include n minus 1 number of edges. Hence our spanning tree will be formed. So with an example, we should explain this algorithm. So for example, let us consider this graph. This is a graph, and here V1, V2, V3, V4, V5, V6, V7 and V8. These 8 vertices are given. One self loop is given and 2 parallel edges here given. Now at first what to do? In the step 1, we convert this given graph to the simple graph. So if we remove all the parallel edges and the self loop, then we will find out this graph. So look, here the self loop is given, that we should remove, and here the parallel edges are given, that we should remove. So this one is the simple graph which we will find out. Now in the step 2, we should choose any vertex as the root vertex. So here we have chosen this V1 as the root vertex initially. And we should put this vertex to the leveling value 0. This vertex should put the leveling value 0. Next, what to do? We should find out what are the incident edges. So in the vertex V1, the incidenting edges are this one, and this one. So according to this 3, so the incidenting edges, this one is first, then this one is second, and this one is third. So if we include these 3 incidenting edges, then we will find out inclusion of these 3 edges will not create any cycle. So that we can include V2, V3, V7, these 3 vertices now, and we can put the leveling value to them as 1 because it is in the first level. After this leveling value, now we go in order. That means in the first vertex, it is let us consider the vertex V7. Now with V7, the incidenting edge is this one. So for this edge, we should consider this one, and if we include this one, then it will not forming any cycle, so we can include it. But this one is also the incidenting edge with V7, and we can't include this one because if we include this edge, then it will form a cycle in the graph, so we can't include this one. Next, come to the vertex V3. With V3, the incidenting edges are all those. So here we can include this one because it will not creating any loop. This one we can add because this one is not creating any cycle. But remaining we can't add because if we add this edge, then it will create the cycle. This one also, if we add, then it will create the cycle. So we can create that only. Next, vertex V2. With V2, this one is the incidenting edge, but we can't include this one because inclusion of this edge will create the cycle. So that's all in the first stage. All the level 1 vertices have considered, and we include the corresponding edges as possible. Now, these vertices should be keep the leveling value as 2. After that, we again do the same process. So V6 with, if we consider, then we will find out this one is the edge which we can include here. This edge we can include here because it will not create any cycle. Next, for the V8, there are no incidenting edges, so it will not possible to take anything. For V3, this one is incidenting, but if we take this one, then it will create the cycle because we already taken this edge. So no more edges can be taken, and we can put the leveling value 3 to this vertex. So finally, we will get the spanning tree as this one. So if we draw the spanning tree, then it should be with V1, this edge connectivities. Then this one, this one, this one, and this one. So look, this one is the spanning tree which we will find out from this graph. So similarly, if we consider the same example, here the same graph and the simple graph only we have taken here. Same example with the different initial point. Initially, or the previous example, we considered V1 as the starting vertex or the root. But now if we consider V3 as our root, so we should put the leveling value for V3 as 0. Now in V3, which edges are incidenting, that we should consider. So V2 is an incidenting edge. Then V1 with, we will find out an incidenting edge. V8 with, we will find out an incidenting edge. And V7 with, we finding out an incidenting edge. So we should include all these 4 edges. Not only that, we can include this one also because no cycles yet to be formed. So that we put the leveling value for all those vertices as 1. Now, one after another, we consider if any edges can included in this vertices. So now if we consider the vertex V1, V2, then here no edges are incidenting. So which we can include, because if we include this edge, then it will create the loop, creates the cycle. So we can't include this one. Similarly for V1 also we can't include any edge. From now it is V7, definitely we can include this one, because inclusion of this edge will not create any cycle. Now from here V8 no edges are there incidenting. From V4 we can include definitely this one, so that the leveling values for this one is 2 and 2, and hence we cover all the vertices, so that our spanning tree is now ready. And the spanning tree for this given graph is now, it is, if it is our V3, then it is V7, then V1, here it is V2, then it is V8, and it is V4. Now from V7 to V6, and from V4 to V5. Hence this is our spanning tree. One more form, or the example, you can say the same example, same graph again, but again with a different initial point. Now let the initial point is our V6. So with this V6, the incidenting edges are this one, and here it is this one. So accordingly we should put this one is the leveling value 0, and these two have the leveling value 1. So now with this one the incidenting edge is this one, and with this one the incidenting edge is 1 and 2. And look, inclusion of all those edges will not create any loop, so that we put these vertices as the leveling value 2. Now with V1, having these two are incidenting, but we can't take this one because it will create the cycle. So that from V1 we can take this one, yes, and that's all. Then with V3 we can't take this one as well as this one, but we can take this one. So now look, we have covered up all the vertices, and these vertices having the leveling value 3. Hence we able to form the spanning tree. And the spanning tree is, if we draw accordingly with this one as the root, here this one is the root, so this is V7, this is V6, this is V5, and then the V4, here it is V1, then it is V2, and here it is the V3. So look here, 1 2 3 4 5 6 7, one more, that is this one, 8 vertices included, and 1 2 3 4 5 6 7 edges are there. In a tree we know if n number of vertices are there, then the total number of edges are n minus 1, that is 7. So you can find out that for all those spanning trees we will find out that if n number of vertices, that is 8 vertices are here, and in each and every spanning tree there are exactly 7 number of edges are included. Hence for the same example, we may have the different spanning trees depending upon our initial choice of root. So in this way we can find out the spanning tree, and this is the proper way. This algorithm is called the breadth first search. So this algorithm to find out the spanning tree. Hello students, welcome to my YouTube channel Easy Mathematics. In this video lecture we are discussing another algorithm to find out the spanning tree for an undirected connected graph G, and the name of this algorithm is depth first search. So the steps to find out the spanning tree by using these algorithms are as follows. The first step is discard all parallel edges and self loop from the given graph G. That is exactly like the previous algorithm. Whatever be the graph is given, we should convert the given graph as a simple graph. In the second step, choose any vertex from the G as a root in such a way so that from VK we can consider as the initial vertex. So such that from VK can make a longest path. It is not necessarily. What does it mean? From the given graph, we should choose one vertex as the root or initial vertex in such a manner so that this vertex from we can create the longest path in the given graph. It is longest, I am telling you, but not necessarily longest, but apparently looks like the longest path. You can choose anything, any path, no issues. But we try to choose such a path so that which one creates the longest path, so that the next number of steps will be reduced. Now in the third step, make a path starting from this initial vertex or the root vertex as long as possible by successively adding edges and vertices. So starting from the vertex VK, we create the path. Let the name of the path is P1 and it will be ended up to the vertex VP. In between there are more vertices. Now after creation of this first path, what we will do? If the path P1 contains all the vertices of G, then the subgraph consisting of this path is the spanning tree of G. If not, then go to the next step. So what we will find out here? If this P1 consists all the vertices of the given graph, then this path P1 is itself is the spanning tree. But if it will not contains all the vertices of G, then we should go for the next step. So what is our next step? So for the next step, it is called the backtracking. So backtracking is the next step. How to backtrack? That is along P1, that is along the path P1 from VP. VP is the end point of this path P1. We will just start back traversing. For example, suppose this one is the given graph. This one is the given graph. This is our initial vertex VK and we have started like this pink curve. So this one is the longest path which we have created and the last point is VP. Now from VP we start the back traversing. So VP to this vertex we should come back. But here no other way to move. From this vertex to this vertex, again no option we have. This vertex to this vertex we should come and this vertex is, say it is VA. Now in this vertex our P1 path should go like this one, but from here we have some another way to move. And just remember that these vertices are not included in P1. So from P1 we will finding out a new path. So that path is, we can move like this way in this yellow line. So this one is the new path. So that along P1 from VP, if VA be the first vertex from which we can make a new path containing no vertex of P1. So from VP we start back traversing. While we reach at VA, then we will find out a new path, and this new path, some vertices are included. These vertices are not the part of the path P1. So this new path we should named as P2 and its starting point is VA and its end point is VM. Okay, so after this one, now start the backtracking from VM. So after getting up to this point, we should again start the backtracking from this one because now this is the end point. So from VM, if we backtrack, then we can come here. From this one, again we will find out a new way to go. If we take this one, then this vertex is the part of P1. So that we can't include this path, because if we include this edge, then it will create the cycle. That's so why we will omit all those vertices which are already the part of selected path. So that from here to here we should come, and from here to this way we can't move because this vertex is the part of P1. So what we will do? We will come back here. After BA, again we should start our journey of backtracking. So from BA to this one, again this one to this one, so we will come to the vertex BB. From BB, again we will find out a new path. So this is the orange path. So this path if we include, then look, these are the again new vertices which are not the part of P1. So that we take this one as a new vertex. Remember, from here Vn is a vertex. From Vn to Vk we can't move because Vk is already the part of P1. So that we have to stop up to here. So this one we can say is the path P3. So we will find out this another path. So which does not contain any vertex from the path P1 and P2. This P3 path will not contain any vertex from P1 as well as P2. So after this way we find out all possible paths from the given graph. So continuing this process may get the paths P4, P5, P6 and all. So what we will now do? We stop the process when each of the vertex of G should include in some of the paths P1, P2, P3 and all. So what we will do? We will traverse the graph in this way and we create the different paths. If all the paths were all the new paths we have discovered, these paths if include all the vertices of the given graph, then we have done. Now what is our outcome? That we will find out for this particular graph, or this is a general graph. For this one we will have the different paths. So this is the P1, then P2, P3. In this way we will find out all possible paths, and finally we just together these all paths together form the required spanning tree. So now how to create this spanning tree? For that I am again giving you one example here. So suppose this one is the given graph. So from this graph, at first we create the graph which should be a simple graph, so that we should remove the parallel edges and the self loop if exist in the graph. After getting this one, what we will do? We should consider any vertex as the root. But remember, the vertex chosen should be in such a manner so that we can create the longest path. As per my knowledge or my mind says that if I consider the vertex V1, then V1 to V2, V2 to V3, V3 to V4, V4 to V5 and V5 to V6 may be the longest path. So that as a path P1, we consider this one, this path. So this is our P1 path. Next what to do? Next we should start the back traversing. So for back traversing, our first vertex is V6. So here the V6 is our vertex from where we start the back traversing. So V6 to V5 we should move. When we come to V5, then from here we will find out the new way to move. So we can move towards this vertex. This is V8. Here this V8 is the new vertex which is not included in this path P1. So that we create another path P2 which is from V5 to V8. So we will have created this one. After getting this V5 to V8, we should again start back traversing, and this time our back traversing point should be V8. So from here we again come back to V5. From here again we will find out a new path. So that is up to V7. V7 is again a new vertex for the given graph. So that we create another path P3 which is from V5 to V7. Now what we will have? V5. Again from V7 we come back to V5. From V5 to now it is V4. From V4 to we have a new path that is up to V1. But V1 vertex is already included in P1. That's why we can't take this one as a new path. So from V4 to we come back to V3. From V3 to it is V2. From V2 to it is V1. That is our starting point. So we have to stop here. After stopping this one, we finally get these three paths. One is P1, then it is the P2 and then it is P3. Finally, if we add all these three paths, then we will find out our desired spanning tree. So this is our spanning tree from the given graph. We use the DFS algorithm to find out this spanning tree. So we come to know about two algorithms to find out the spanning tree. One is the BFS and another one is the DFS algorithm. So which one you find easy, you can opt this one, or in fact both are easy. You can go for both also. So these are the two easiest way to find out the spanning tree from the given graph. In our last two lectures, we come to know about two algorithms. One is the breadth first search and another one is the depth first search to find out the spanning tree from any given undirected connected graph. Now we are going to find out the minimal spanning tree. We know what is the minimal spanning tree. So now any graph is given and the graph is the weighted graph. Then with the weighted graph, how to find out the minimal spanning tree? Minimal spanning tree means which have the minimum weight, or the shortest spanning tree also we can say. The total weight of the tree, spanning tree, is minimum. Then how to find it out? That is a big issue, because from a given graph to find out just a spanning tree is easy, much more easy. But if we want to find out the minimal spanning tree, then we have to measure all the weights according to the ages included. So how to find out the minimal spanning tree? For that we have the algorithm, and the name of this algorithm is the Kruskal's algorithm. So the steps for the Kruskal's algorithm are as follows. So the first step is, any graph is given, that graph should be a weighted graph, and from this weighted graph any parallel edge and self loop if exist, then we should remove them. Remember, while removing the parallel edges, you should check that among all the given parallel edges, which edge having the minimum weight, that edge we should keep in the graph, and the remaining parallel edges we should remove, because our target is to find out the minimal spanning tree. Now in the second step, make a list of all edges of G in order of increasing weight. What we will do in next? Whatever the edges are there in the simple weighted graph, no parallel edges, no loops are there in that graph, whatever the edges are remaining, now we just arrange all those edges according to their weights. After arrangement of this one, what we will do, from this list, select an edge having smallest weight. From this list, what is the first edge? That means which edge having the minimum weight, that edge we should select as the first edge in the minimal spanning tree. So from the list of edges, select an edge with smallest weight that makes no cycle with the previously selected edge. What we will do next? After selection of the first edge, we should go for the second selection. So in the second selection, you just remember that we should select only that particular edge which have the minimum or the small weight, and what edge initially we have chosen. From this edge, one edge means it have two endpoints. Among these two endpoints, any one endpoint should be connecting or should be there in the chosen edge. So in this way, we just continue the process until total n-1 number of edges should be included in the tree. And after that one, we will find out the required spanning tree, which one should be the minimal spanning tree. So now, these selected edges constitute the minimal spanning tree. How to find out this one? For that, with an example, if we will solve this one, I hope we can understand better. So one example, for here the graph is given. From this graph, we are going to find out the minimal spanning tree. Here remember that A1, A, B, C, D, E and F. These are the total 6 vertices given, and the corresponding weights are given in the graph. At first, what we will do, we convert the graph to the simple graph. Here this one is the self loop which should be deleted. Now the parallel edges are here. So here 3 edges are given with weights 2, 4 and 7. So very obvious, we keep the edge with weight 2 and remove the edge with weight 7 and 4. After this removal, we will find out this one as the simple weighted graph. This is our step 1. Now in the step 2, what we will do? We just write all the edges according to their weights. The increasing weights we should write down. So just look here. First edge is weight 1. Here 1 and this is 1. So AD, this edge having weight 1 and AF, this one having weight 1. So we should write in the first AD as weight 1, AF as weight 1. Next weight 2 for this one and this one. So DE and EF, these two having the weight 2. DE having 2 weight, EF also having weight 2. Now the weight 3 for the edges, this one and this one. So AB, AC and BC, these 3 edges having weight 3. AB, AC, BC, all these 3 having the weight 3. Next it is the weight 4 for CD, CF and AE. So we should write initially AE, then it is CD, then it is CF. So AE, CD, CF, all this having the weight 4. One more edge is left, that is BD with weight 5, that we should write next. I have the scarcity of space, that's why I have not written that particular one, but you should write. So these are the all edges of the given graph with corresponding weights. After getting all this, this is our step 2. Now in the step 3, what we will do? We should choose the first edge with the weight. That is AD should be chosen as the first edge. So now look, AD means AD. AD. So that in the step 3, we should choose AD as the first edge. After that, here next edge is AF. So AF is this one. So if we choose AF, then definitely it will not create any cycle. So in the 4th step, AD is the first step, then AF should be included here. Both the weights are 1. After that, the next edge is DE. DE means here the D is present. So D present and its weight is 2. So DE means this edge. So we should include this one because this one also not creating any cycle. So that in the 5th step, we include the edge DE also. After this one, we have EF. So if we include EF, then it will create the cycle. So that we can't include this one. This edge we can't consider. So EF we can't consider. Now next edge is AB. AB having the weight 3. So come back again here. AB means this edge. So if we include this one, then again it will not creating any cycle. So in the next step, in the step 6, we will find out that AB if we include, then this is the previous part and this is the new part. So it will not creating any cycle. After that AB, it is AC. AC having the weight 3. If we include AC, then this is again not creating any cycle. So in the next step, in the next 7th step, if we include AC, then we will get this one. So now look, here total 6 number of vertices and we have included 1, 2, 3, 4 and 5 edges. So that done because all the edges, all the vertices of the given graph we have already included. So now the remaining edges, after AC it is here BC, AE, CD, CF and one more that is BD. Whatever the edges are there, if you want to include these edges, then you will find out that these are definitely creating the cycle. It is not possible to add any of these edges. Just for observation, look at this one. It is BC. BC is the edge, this one. If we include here BC, then it will create the cycle. After BC it is AE. If we include AE, then it is also creating the cycle. So after inclusion of the edges, one less than the number of given vertices, if we going to include any other edge, then definitely we will create the cycle. So that now we have to stop the process. And this one is our the minimal spanning tree. So this is the required minimum spanning tree and its weight should be 1 plus 1 plus 2 plus 3 plus 3. So that is 1 plus 1 plus 2 plus 3 plus 3. That is 10. So the minimum spanning tree which we can find out from this given graph with weight 10. So this is our result for this example, and this is the way how to find out the minimal spanning tree by using the Kruskal's algorithm. In this lecture, we are going to discuss the Prim's algorithm to find the minimal spanning tree. Let G be a given weighted graph with n vertices. We have to find a minimal spanning tree in G. There are several methods available for finding a minimal spanning tree in a given graph. One of the algorithm is Prim's algorithm. In previous lecture, we have discussed one more algorithm to find out the minimal spanning tree, and that one is the Kruskal's algorithm. So now it is the Prim's algorithm, and here the steps how to find out the minimal spanning tree by using the Prim's algorithm. So the first step is, as usual, it is the discard all the loops and parallel edges with higher weights from the weighted graph G. Next, tabulate the weights of the edges of G in a n cross n table where n is the number of vertices of G. So what does it mean? Let this one is the given graph. Here the total 4 number of vertices are given, V1, V2, V3 and V4. These 4 vertices with, we create a table where row wise we put V1, V2, V3, V4, these all vertices, and column wise also we put the vertices V1, V2, V3 and V4. Basically this one creating a 4 cross 4 matrix. So at first, depending upon the number of vertices, we should create such matrix. After that, what about the entries of this matrix? For that, we should put the value 0 corresponding to the edge joining the vertex Vi to Vi. Vi to Vi means V1 to V1, V2 to V2, V3 to V3, V4 to V4. That means V1 to V1 joining means there exists a loop, but in the graph we initially discard all the self loops. So if these entries we will find out, here look, V1 to V1 means this position, then V2 to V2 means this position, V3 to V3 means this position, and V4 to V4 means this position. So corresponding to all those diagonal entries, we should put the value 0. Next, put the value infinity if there is no edge between any two vertex Vi and Vj. From the given graph, if you will find out that in between two vertices there is no edge connectivity, then corresponding to that position we should substitute the value infinity. For example, here it is V1 to V3. These two vertices are not connected by any edge. So V1 here and V3 is here. So V1 and V3 corresponding to this one. So V1, V3, that means this position should be entered as the value infinity. Similarly, V3 to V1 also put the value as infinity because these are having the no edge connectivity. Now, if in between the two different vertices there is an edge connectivity, then we should put the given weight corresponding to the given edge. So that edge we should denote it by Wij. Wij in general we put the weight depending upon the vertices chosen. So here if we consider the first row, then we just look V1 to V2. V1 to V1 it is 0. Then V1 to V2, there is an edge connectivity and its weight is 2. That means W12 is the corresponding general weight and its value is equals to 2 for this particular given graph. Now V1 to V3, as V1 to V3 no edge connectivity, then this value should be infinity. And V1 to V4 again it is connected, and this value is equals to 5 because the given weight is 5. Similarly, now come to the vertex V2. So V2 to V1 it is connected and its value is 2. So it has to be 2. Then V2 to V2 should be 0. Then V2 to V3 it is connected and its value is 3. So that we put this value as 3. Now V2 to V4. So V2 to V4, the connectivity is there and its weight value is 1. Hence, this value should be 1. And likewise, we just find out the corresponding spaces where we should put the corresponding weight depending upon the connectivity of the vertices. So in this way, we should make a table from which we calculate the minimal spanning tree. So this table is very much important to create. So at first, we should create this table for the simple graph. Now, after creating this table, we should start from the vertex V1. V1, that means it is the first row of the table. Now what we will do? We connect this V1 to the vertex which has smallest entry in the first row of the table. So we just observe the entire first row of the previous table. In this table, we should observe the entire first row. Among this all first row entries, which value is the smallest value? Definitely 0 we should not consider because these are the diagonal entries, and infinity is the any value, so we should not consider infinity also. So any value if it is given, then we should consider which one is the minimum. If we consider this one, the first row, then its first entry is 0, second entry is 2, third entry is infinity, and fourth entry is 5. So the minimum value is 2. That's why we should select this position, and this position is the connectivity with V1 to V2. So what we will do here? We connect V1 to the vertex which has smallest entry, the first row of the table. Then let that vertex be Vk in the first row. That is in general. We generally let us consider the vertices are from V1 to Vn. Among these all vertices, we have considered that in the first row corresponding to the vertex Vk, V1 Vk, this particular entry having the minimum weight value. So we should select that one. In the next step, we should search for the smallest entry in the rows V1 and Vk. Once we have started from V1 and we selected the Vk entry, Vk corresponding the vertex Vk, just look here, we have started from V1, then let corresponding to Vk, we will get this one is the smallest entry. So that here Vk is also one of the row. So V1 is one of the row and Vk is the another row, definitely. So among these two rows, we should find out the next smallest entry. But remember here, while we choose the smallest entry in V1 and Vk, that time we should not choose any of this column and this column because V1 and Vk, these two vertices already has been selected. So once a vertex has been selected corresponding to that particular vertices for, the columns should be omitted for the choice of minimum weight. So V1 and Vk, among these two, after omitting these two column entries from the remaining options, that means remaining option is these are here, this one and this one and this one and this one. From these options, we should search that which one is the minimum weight value. Corresponding to that minimum weight value, we should decide. Let Vj is the minimum weight value, we will find out. So we should select this one. So the next vertex chosen is Vk, Vj. So that is the edge which we should choose in the spanning tree. So after choosing of this one, in the next step, what we will do? We consider the column V1, Vk and Vj. Remember which row we have taken previously. While we choose one vertex as the entry vertex, we should include one extra row corresponding to that chosen vertex. but we should not leave the previous rows even. What we will do, we just leave the corresponding columns as the rows are increases. So in the next state, we search for the smallest entry in the rows V1 and Vk by omitting the columns V1 and Vk. Let Vj be the selected vertex with smallest entry in the two rows V1 and Vk. Hence, the first two edges have been selected. Next, we consider the row corresponding to V1, Vk and Vj to find out the smallest entry by omitting the columns V1, Vk and Vj. So let Vi be the selected vertex with the smallest entry. So continue this successive steps of selection of vertices until n-1 edges are selected, because we know if we are going to create the spanning tree, in fact the minimal spanning tree, then with n number of vertices there should be n-1 number of edges. So this is the process by which we can select all the edges to require to form the minimal spanning tree. So these edges constitute a shortest spanning tree or minimal spanning tree. Finally, we should add the weights of the selected edges to get the final weight of the minimal spanning tree. One thing you should remember, that there may be more than one minimal spanning tree in a graph. So the entire algorithm we should discuss with an example. So what is the example? Here the find by the Prim's algorithm a minimal spanning tree from the following given graph G. So the graph is given this one, and observe here the vertices are A, B, C, D, E, F and G. So total 7 vertices are given. So corresponding to this vertices and in this graph we will find out no parallel edges and self loops are there. So this one is a simple graph. So with this simple graph we at first create a table. The table means this is the matrix where row wise and column wise we put the vertices. So here all 7 vertices are put it, and all the 7 vertices put it over here also. Now the corresponding entry for, we know that the diagonal entries are always 0. So look, all the diagonal entries are 0. In fact, we can draw the diagonal in this way. So look, all the diagonal entries are 0. Now corresponding to the vertex A, we should start from one after another. So let us start from the vertex A. So A to A there should be the entry 0. A to B there is no connectivity, that's why it has to be infinity. Then A to C again no connectivity, so it should be infinity. Then A to D there is a connection and its value is 6, that's why this is the 6. A to E its value is 14. Then A to F its value is 8, and A to G its value is 6. So from A, what are the connectivities for all other vertices that we have recorded? Now come to the vertex B. So from B to A there is no connectivity, so it should be infinity. B to C it is 4, B to B definitely 0, then B to D it is 10, then B to E no connectivity, so it is infinity. B to F again no connectivity, so infinity. B to G it is connected and the weight value is 6, so it is 6. Likewise, we just put all those entries and just observe this matrix carefully. You will find out this one is a symmetric matrix. Just observe if this one is the diagonal, then you just find out that this one is the symmetric matrix. Just look, if we think this one is the mirror, then we just find out the mirror image of this one. So this is the table which we should form by the given graph. After formation of this one, now we should find out the spanning tree from here. So what we will do, we should start from the first row, that is the row A. So in this row A, at first we find out what is the minimum entry. What is the minimum entry? So minimum entry is here 6. But 6 we will find out at two places, at the place D as well as G. If you will have such a tie, then you may choose any one of these two. So initially let us choose the first chosen vertex is D. Any one we may choose, and we choose it is as 6. So that here from the first row consider an edge AD. So look, we should consider AD because this is the entry AD. So we have taken here the AD. Now the row A and row D we should consider for the next. So row A means this one. Row A is this one. And row D means this one. Among these two, we should omit the first column, and the D column, because we already have chosen these two vertices. So now from the remaining means the entries are these two, here these 3 and these 2 and these 3. Among these entries, which one is the minimum value? So the minimum value here we will find out that it is 6 only. So 6 means this position for AG is the next choice of the edge which we should select in the spanning tree. So AG is the next choice for the selection, so that we should write down here from the row A and D, select the edge AG. Now what we will do? We will have now 3 rows for our choice. One is A, second one is D, and another one is the G. So G means this one. So here G we have taken, and we should omit this column because this column we should not consider now. So omitting these 3 columns and considering these 3 rows, what we will find out here? We will find out that the minimum entry corresponding to here, it is 4. So the minimum entry we will find out here, it is 4. So 4, this position is the GF. So that we include next the edge GF, means this one. Next we include this edge GF. So in the next consideration, we consider this one, this row also, and we definitely remove the A column corresponding to the vertex F. So after this removal from the remaining portions, what is the minimum entry? The minimum entry is now it is 6. So this one is our minimum entry. So this position is GB. So next we include the edge GB in your spanning tree. So that after that the B is selected and B column should be omitted. So B is included and B column is omitted. Now from the remaining portions, what is the minimum value? So at first we just observe here that A, D, then G, F and B, all those vertices already selected. Our remaining is C and E. So that we should emphasize on the column C and E only. So here in the selected rows we will find out that this one is the minimum entry. This one is the minimum entry. So that is the position BC. So that we consider this edge BC in the spanning tree. So after doing this one, we consider this one also for our choice of selection, and we omit this column again. So now the remaining column from where we should find out the next minimum is the only E, because only the vertex E is left. So here the minimum entry is the 12. So this corresponding we will find out the next edge. So this position is DE. So we should include next the edge DE. So this one is our next edge in the spanning tree. So after doing this one, we will selected all those vertices. That means all those rows from we have the entries. So for all vertices we have the entries. So finally we get our spanning tree. And here all the yellow lines constructing the spanning tree. So just look the summation here. So from the first row we consider AD. From the second row, that means not second, in the second step from row A and D we select the edge AG. From the row AD and G we select the row GF. From the row AD, G and F select the edge GB. And from the row AD, G, F, B we select the edge BC. And from the row A, D, G, F, B and C we select the row DE. So by considering this one, we finally create our minimal spanning tree like this way. And the minimum weight is 6 plus 6 plus of here 4, then plus 6, then plus 4 and plus 12. So finally it is the 38 is the minimum weight value for the given graph, from where we will find out the minimal spanning tree. So this is our Prim's algorithm to find out the minimal spanning tree. Hope it is not that much difficult. Just go through the video once again to understand the entire process. Step by step evaluation is given here. I hope you understand. In this video lecture, we are going to discuss about a very important topic of graph theory. These two topics are the rank and nullity. So there are so many questions that what is the rank for a graph or the nullity of a graph? So for that, at first we should come to know about the fundamental numbers. Basically, in a graph, there are few things which are very important. So to define a graph G, the most important things to know are the number of vertices, that is n suppose, then the number of edges, that is suppose it is E, and the number of components, that should be suppose it is K. If K is equals to 1, then G should be connected, otherwise it is disconnected. If K is 2, 3, 4 or anything, then we should say that G is a disconnected graph. Now since every component of a graph must have at least one vertex, so that we can say the total number of vertices in a graph should be greater than or equals to the number of components. So now one individual component is a connected graph. Hence each component consists m minus 1 number of edges at least if m is the number of vertices of the component. That is very obvious. If any component having m number of vertices, then at least it should have m minus 1 number of edges to keep it connected. So we can say em, that is the total number of edges in the given component, should be greater than or equals to m minus 1. So for the entire graph G, we can say it should be the total number of edges greater than equals to n minus k. K is the number of components, n is the total number of vertices. So now again it is very obvious that n minus k should be greater or equals to 0. Total number of edges in a graph, this is definitely not a negative number, so that it has to be either 0 or greater than 0. And so E minus n plus k is obviously again greater than equals to 0. We will find out from here E minus n plus k should be greater than equals to 0. These numbers, so the numbers n, e and k, the number of vertices, number of edges and the components are independent also. One never affects the other. Number of edges not affect the number of vertices and doesn't affect the number of components. These three numbers n, e and k are called the fundamental numbers in graph. These are very important. These three numbers n, e and k, number of vertices, number of edges and number of components, are called the fundamental number in the graph. So without knowing any one of them, we cannot draw any graph. It is again very true. If you want to draw a graph completely, then you should know the number of vertices, number of edges and the graph is connected or not. Then only you can draw a graph properly. Now, how these three numbers are related among each other, that we are going to discuss. So here, these fundamental numbers of graph are derived two other important numbers. One is called rank and another one is called the nullity. Where the rank is, rank denoted by R, the rank value is n minus k. And the nullity is E minus n plus k. So if the graph is your connected graph means k should be 1. So if your connected graph is there, then k is equals to 1, so that for any connected graph you will find out the rank is equals to n minus 1 and the nullity is E minus n plus 1. So in any graph the rank is n minus 1. n minus 1, this term is I think very much known to us. n minus 1 is the number of edges in a tree with n number of vertices. That means to keep a given graph connected, how many minimum number of edges are required? That number is the rank. And what is the nullity? Nullity is the remaining edges which are not included to keep the graph connected. So what we can say, the rank of a connected graph is n minus 1 and the nullity is E minus n plus 1 if the graph is connected. Here you should note one thing, that is the nullity of a graph is also referred to as the cyclomatic number or first Betti number. And one more observation is that if we add the rank and nullity, then we will find out the total number of edges. Just look, rank is n minus k and the nullity is E minus n plus k. If we add these two, then we will find out n cancel, k cancel, and it is E. That is the total number of edges in the given graph. So now for the spanning tree, T of G, the rank of G is equals to the number of branches in T of G. And the nullity of G is the number of chords in G. That is again very obvious. We know that how many edges are included in the spanning tree. These are called the branches. And those edges which are not included in the spanning tree from the graph G are called the chords. So that the branches are the rank and the chords are the nullity. And if we add the rank and nullity, we will get the total number of edges. Next, one more important thing in the graph theory is the fundamental circuit. So what is fundamental circuit? So this fundamental circuit also generated from the spanning tree. So a circuit formed by adding a chord to a spanning tree T of a graph G is called a fundamental circuit of the graph with respect to the spanning tree. What we will find out here? What is fundamental circuit? At first it should be a spanning tree. In spanning tree, the number of edges included, these are the branches. And the edges which are not included in the spanning tree from the graph G, these are called the chords. Now, in the spanning tree, if we introduce any one of the chord, then we will find out definitely a circuit is formed. That circuit is called the fundamental circuit. Here one thing again should be noted, that if T be a spanning tree in a connected graph G, then G has n vertices and E edges. Then there exist E minus n plus 1 number of fundamental circuits formed by T. It is again very obvious the total number of chords are the total number of fundamental circuits which can be formed from the given graph. So, how to find out this fundamental circuit? So, with an example, we will find it out. Let this one is the given graph and we are going to find out the fundamental circuit of this graph. So, at first, whatever be the graph is given, we just remove the self loop and the parallel edges if exist. Here, this one is the self loop and these are the parallel edges. So, one of them should be deleted. So, after deletion of this one, as a simple graph, we will find out this one. Now we know how to find out the spanning tree from this given graph. So there are breadth first search algorithm or depth first search algorithm to find out the spanning tree. Any algorithm you may use to find out the spanning tree, and finally we will suppose find out this spanning tree. So in the spanning tree, the ages, we have considering the ages from this one, and this ages are included. These ages are included. So just look, these ages are included. So the ages which are not included here is either from V2 to V3, or from V2 to V4, or from V4 to V5, or from V3 to V5. Otherwise, it is from V6 and V5. So these are the corresponding chords in the given graph. So look, these are total 5 chords. In the given graph, total number of vertices are 7. And in the spanning tree, then definitely total 6 number of edges are included. And in the given graph again, the total number of edges given are 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10 and 11. So total number of edges are given as 11. So in this graph G, N is the 7, the total number of vertices. E is 11 after definitely removing the parallel edges and the self loop. So that we say the rank of G should be 6. And the nullity of G should be 11 minus 6, that is 5. So that from this given graph, we can create total 5 different fundamental circuits. These circuits are either we can join V2, V3, that is the one of the circuit formed. Then otherwise we can join V2, V4, one more circuit. Then V3, V5 we may join. Otherwise we can join V4, V5, or we can join V5, V6. So in this way, the different fundamental circuits can be formed. So this particular spanning tree T having the 5 fundamental circuits. So for different spanning trees of G, the different fundamental circuits may be found. For the given graph, if we draw some other spanning tree, so then other different fundamental circuits we will find out. So this is just the basic concept of fundamental circuit and the rank and nullity. In this video lecture, we are going to cover an entire chapter of graph theory, that is cut set and cut vertices. This chapter is really very important because this chapter have the immense application for set up the network of different cities or different areas. So at first we come to know what is cut set and cut vertices. After that we discuss some applications of these cut sets and cut vertices. So what is cut set? In a connected graph G, a cut set of edges whose removal from G leaves G disconnected, provided removal of no proper subset of these edges disconnects G. So, for example, if we want to explain this cut set, then let us consider one example here, this one. In this graph, we have total 8 vertices, V1, V2, V3, V4, V5, V6, V7 and V8. And here the corresponding all edges are given. Total 12 number of edges are here. All the edges have a specific name, E1, E2, E3 up to E12. Now we are going to find out the cut set. For that, what we will do? We just draw any edge in such a manner. Edge means we just put a cut in the graph. So for example, if we put this one, this is a cut in the graph. We just separate the graph into 2 parts. So in this cut, which edges are included? Here E7, then E11, E12, then E10 and E4. All those edges are belongs to this cut. If we delete these edges, then what happens? We will find out the graph of this way. If we delete all those edges, then the remaining part is this one. So that is, and here from this part. So this part is there. So just look, after deletion of these edges, we will find out the graph becomes disconnected and we get one extra component to the graph. Here the only one graph, connected graph, no components are there. And here after this deletion of edges, we will find out the 2 components of the graph. So if we write these edges in the set notation, so here if we write in this way, so this one includes all the edges E4, E7, E10, E11, E12, all those edges which are on this cut partition. So this one is called the cut set. Here in this graph, not necessary that only this one is the cut set. In fact, so many cut sets we can form from here. We may put any partition by which the graph becomes more than one component. That means graph becomes disconnected and it creates one more component. Then that partition is the cut set. For example, if we consider this one, then if we cut accordingly, then this vertex becomes separated from the entire graph, and for this separation E5, E10, E11, E6, these edges are included on that. So this one is a cut set. Again, we can put the partition like this one. So here if we put like this partition, then what happens? We may delete this one and this one, so that what happens here? Here we will find out this one becomes the entire graph and this vertex will be separated. So here instead of 2 components we get 3 components. So then here is a specific things will happen. If we create the cut set with considering E1 and E2, then it is no more a cut set, because cut set is that by which only one extra component should be created. So just have a look. For the given graph, we have these all are the different cut sets, E3, E8. Then here E1 is individually a cut set. E1 is individually creating a cut set, not E2 is included there. Again, E2 is individually a cut set. This one is another cut set. So in this way, the different cut sets we can form. But if we consider the set E1 and E2, then this one is not a cut set. The reason is what? The reason is if any cut set for its proper subset, if it creates a cut set, then the set is not a cut set. So if we think of the set is E1, E2, then its subset we can consider as E1, which is a cut set, E2, which is another cut set. So these two are the proper subset of this set. If we will find out any proper subset of a set is a cut set, then the superior set never be a cut set. So according to this terminology, we can say that as no proper subset of a cut set can be a cut set, so cut sets may also be called as minimal cut set or a proper cut set or a simple cut set, even co-cycle too. So these are the different names of the cut set. So in this way, we can find out the different cut sets. Any graph may be given. From there, we just give a partition. It is up to us. According to that partition, whatever the edges are included on that partition, you just write them in a set format. This is your cut set. Now, after this cut set, it is the note on the cut set. What are the special things we will find out from this cut set? That things are, a cut set always cuts a graph into 2 parts. A cut set can be defined as a minimal set of edges in a connected graph. That is also very true. Cut set means here the minimum number of edges which can disconnect the graph. Next, removal of edges of cut sets from the graph G reduce the rank of the graph by 1. What is this? So for that, I'm just giving you one example. If this one is the given graph, then we just put this one as the partition. If this partition we will put, then this one and this one, these 2 edges are included in the cut set. Now what we are going to understand here, that the removal of edges of cut set from the graph reduce the rank of the graph. What we will know about the rank of a graph? Rank means we know if from any given graph we draw the spanning tree, then the total number of edges included in the spanning tree is the rank of the given graph. Here in this graph, total 6 vertices are given. So n is 6 and the total number of edges are 8. And we know as the total number of vertices are 6, so in the spanning tree, there are definitely 5 number of edges. So the rank of the given graph is 5. Now, according to this cut set, if we remove these 2 edges, then what we will find out? Then we will find out this one as the reduced graph. In this reduced graph, n is equals to 6 because no vertices will be deleted, and the total number of edges becomes 6. 1, 2, 3, 4, 5 and 6. And the rank of this graph is what? So the formula for the rank we know, that is n minus k. N minus k means that is the number of component is k. So n is 6 and the k is 2 here. So the value is 4. Previously the rank of the graph is 5. Now the rank is 4. So if we just give a cut set here, so after removal of the edges from the given graph, according to the cut set, the reduced graph having the rank 1 less than the original graph. It is always happens. Now one more thing which we can say about the cut set is a set of edges together with their end vertices constitute a subgraph. A cut set in G is a subgraph of G. So if we can find out the cut set, so that cut set means only the edges are there. Those edges including with their end vertices, if we draw, then the graph which we will find out, that one is the subgraph of the given graph. So for example, here the graph is given, these two are the cut sets. So these 2 edges have the end vertices as this one 2, 3 and here 6. These 3 are the end vertices for these 2 edges. So if we draw this one as the graph, so this one as the graph, then this is the subgraph of the given graph G. That is very obvious. Next it is, since removal of any edge from a tree breaks the tree into 2 parts, every edge of a tree is a cut set. What is given here? Removal of any edge from a tree breaks the tree into 2 parts. That is very obvious. We can say this one even a tree. If we remove any edge, then what happens? It becomes disconnected. So that we can say that removal of any edge from a given tree makes the tree disconnected. Hence, any edge is the cut set for the given tree. These cut sets are of great importance in studying properties of communication and transportation networks. Suppose, for example, if we consider this graph, here total 8 number of vertices are given. So this 8 vertices, suppose represents 8 cities connected by the telephone lines. Now we wish to find out if there are any weak spots in the network that need strengthening by means of additional telephone lines. So what we will do, we look at all the cut sets of the given graph and the one with the smallest number of edges in the most vulnerable. So here, now it is the fundamental cut set. Let T be a spanning tree of a connected graph G. A cut set S of G containing exactly one branch of T and rest edges in S are chords with respect to T is called a fundamental cut set of G with respect to T. If we consider this one as the graph, then the fundamental cut set for how to find it out? At first, whatever the graph is given, from that graph we can draw or we can find out a spanning tree. In the spanning tree, here in this graph, this is the spanning tree. The pink line is the spanning tree. In this spanning tree, if we draw the cut sets, in fact the fundamental cut sets, then the fundamental cut set should contain at least one branch, in fact exactly one branch one branch from the spanning tree and the remaining are the chords from the given graph. So for example, if we consider this one as the partition or the cut set, then this will include only one branch from the spanning tree and the remaining two are the chords. Likewise, if we consider this one as the cut set, then one branch, one chord. If we consider this one as the cut set, then one branch, two chords. If we consider this one as the cut set, then one branch and two chords. We can consider this one as the cut set where one branch, two chords are there. So in this way, we can cover up all the fundamental cut sets. So beside fundamental cut set, definitely there are more cut sets may be present, but the fundamental cut set means one branch and the remaining chords should be there. So if a spanning tree we draw from a graph, then depending upon the spanning tree, the number of edges represents, that number of edges in the spanning tree represents the total number of fundamental cut sets. So what we observe for the fundamental cut set, so for that every branch of a spanning tree defines a unique fundamental cut set. Every branch of a spanning tree defines a unique fundamental cut set. Number of branch of a specific spanning tree is equal to the number of fundamental cut set for that particular spanning tree. Here for a particular spanning tree, the number of fundamental cut sets are fixed. For the different spanning tree, again these are different. Next it is the number of chords defines the number of fundamental circuits for the specific spanning tree. That we know when we go through the fundamental circuits. How to create the fundamental circuit? In a spanning tree, if we add the chords in the spanning tree, only one chord if the spanning tree we add, then it will create the fundamental circuits. So depending upon the number of chords in a given graph creates the number of fundamental circuits, and every fundamental circuit has an even number of edges in common with any cut set. If we create the fundamental circuit, then with that particular circuit creation, if we draw the cut set, then that cut set have even number of edges common with that fundamental circuit. So what it says that suppose this one is the one of the chord which is included in the graph. With the spanning tree, if we include this one, then this one is our fundamental circuit. If from here we create the fundamental cut set, then we just take this one. Here this one is the branch and this one is the chord. These two are included over there. In the circuit, the edges are E1, E6, E7, and in the fundamental cut set, the edges are E1, E6. So two edges are common, that is E1 and E6 are common in both the fundamental circuit as well as the fundamental cut set. And remember, these two edges, among these two edges, one is the branch of the spanning tree and another one is the chord of the given graph, and that always will happen. Now it is the cut vertex. So what do you mean by the cut vertex? So a vertex V of a connected graph G is said to be a cut vertex if its deletion from G together with the edges incident to it disconnects the graph. So what is cut vertex? If this one is a graph, suppose, then from this graph, if we delete one vertex, and by deletion of that vertex, if the graph becomes disconnected, then the vertex is said to be the cut vertex. In fact, not necessarily only one, but more than one vertex if there to require to delete to make the graph disconnected, then both those vertices are said to be the cut vertices. So if this one is the example, then if we delete this V2, then what happens? We will find out the graph of this type. It is V1, one separated, and another is this one. Deletion of this V2, also delete these edges, because we know without the end vertices, edges have no existence. That's why after deletion of this one, we will find out this one as the graph. So this is a disconnected graph, as it becomes disconnected by deletion of V2, that's why we can say V2 is the cut vertex. Similarly, V3 also we can consider. If we delete V3, then the removed edges are these three. After this removal, our reduced graph becomes this one, which is a disconnected graph. So we can say V3 is also a cut vertex. Not only that, if we remove V6 and V4 both together, then after removal of these two vertices, these four edges are removed. So that part and this vertex is again a cut vertex. So the cut vertex that time is V4 and V6. So this way we can find out the cut vertices. Here the important thing for the cut vertices are a graph may have more than one cut vertex. Then every vertex with degree greater than 1 of a tree is a cut vertex. That should be remembered. Suppose this one is a tree. In this tree, the vertices with degree greater than 1 are the cut vertex. So these vertices are here with degree 1. So if you remove these vertices, then by removal of the vertices with degree 1 will not disconnect the graph. But if we remove this vertex, then these four edges becomes deleted. So it becomes the disconnected. Similarly, if we remove this one, then the graph becomes disconnected. Not only that, if we remove this one, then also even the graph becomes disconnected. So in a tree, every vertex with greater than degree 1 is a cut vertex. Now a graph may have no cut vertex at all. Suppose this one is a graph. Here if you remove the vertices, then you will find out no cut vertex is there, because removal of any vertex or more than one vertex does not make the graph disconnected. That's why this graph having no cut vertices. Next, it is the one more important thing in the cut set and cut vertices, that is the connectivity and separability. So connectivity having two ways. One is the edge connectivity and another one is the vertex connectivity. So what is edge connectivity? The edge connectivity of a connected graph can be defined as the minimum number of edges whose removal reduce the rank of the graph by 1. So edge connectivity means we should find out that particular cut set which have the minimum number of edge among all the cut sets from the given graph. So the edge connectivity of a tree is always 1. That is very obvious. If a tree is given, then its edge connectivity should be 1, because removal of any one edge makes the graph disconnected. Edge connectivity can be possible only for the connected graph. That should be remembered. The edge connectivity can be possible only for the connected graph. And for disconnected graph, edge connectivity is 0 always. So after this one, it is the vertex connectivity. So what is vertex connectivity? The vertex connectivity of a connected graph G is defined as the minimum number of vertices whose removal from G increase the number of components of G. So vertex connectivity is what? Vertex connectivity means if we remove the minimum number of vertices, and by removal of the minimum number of vertices, the graph becomes disconnected, then this one is called the vertex connectivity, like the edge connectivity. In edge connectivity, minimum number of edges, and in vertex connectivity, the minimum number of vertices should be there. So for example, if we consider this one as a graph, in this graph, total 8 number of vertices are given and 16 number of edges are given. Here look, if we remove this particular vertex from this graph, then what happens? We will find out the remaining graph as this one, because these edges will be removed and this one. So these two part remaining after the deletion of this vertex and its incidenting edges. So this one definitely 2 components, and so the vertex connectivity here should be 1, because only one vertex is required to make the graph disconnected. Now if we consider this example, here also the number of vertices are 8 and the number of edges are 16. But here the vertex connectivity is 3. Actually what happens? we just find out that what is the degree of each vertices. Here we will find out the minimum degree for the vertices is 3 in this entire graph. So that we have to delete 3 vertices. So suppose we want to disconnect, and at first we remove this vertex. So after removal of this vertex, these incidenting edges will be removed. After that we remove this one, and then we remove this one. By all those removal, our remaining things will be this vertex and then this part, and the remaining everything will be deleted. Just look. Here is one more example by which we can say that a graph with 8 number of vertices and 16 number of edges, the vertex connectivity is 4, because by removal of 4 vertex it becomes disconnected. So we should note here that the vertex connectivity of a tree is always 1. The above definition is meaningful only for the graph that have 3 or more than 3 vertices and are not complete. This definition can be valid for a graph which have at least 3 vertices or more than 3 vertices, and definitely the graph should not be a complete graph, because if the graph is complete graph, then we have to delete all the vertices, but still we will not find out any disconnection over there. Next, it is the separable graph. A connected graph is said to be separable if its vertex connectivity is 1. So separable means what? If we delete only one vertex from the graph and the graph becomes disconnected, then we say the graph is separable. And here one most important thing is the articulation point. And what is this articulation point? In a separable graph, a vertex whose removal disconnects the graph is called a cut vertex or cut node or an articulation point. So in a graph, if we remove any one particular vertex and after removal of that particular vertex with its incidenting edges makes the graph disconnected, then that particular point is called the articulation point. So in a tree, every vertex with degree greater than 1 is an articulation point. Next, the few important theorems on the cut set and the cut vertex. The first one is the edge connectivity of a graph G cannot exceed the degree of the vertex with the smallest degree in G. Always remember, whatever be the graphs are given, in this graph you just find out what is the degree for each vertices. After finding out the degrees of each vertices, find out which vertex have the minimum. That minimum degree value may be the edge connectivity of the given graph. So for example, for this graph, the minimum degree is 1, so the edge connectivity has to be 1. Just look, any one edge if you remove, then it becomes disconnected. Here also, all the vertices having degree here 3, 3, 3, 4, it is, this is 4, this is 3 and this is 1. So the minimum degree is 1, so its edge connectivity is 1. Likewise, here the minimum degree is 2, so edge connectivity has to be 2. Next, it is the second theorem. The vertex connectivity of any graph G can never exceed the edge connectivity of G. Always the vertex connectivity is either equal or less than the edge connectivity. And the maximum vertex connectivity in a graph G with n vertices and e edges is the integral part of the number 2e by n. So 2e, e means the number of edges and n is the number of vertices. If we write 2e by n and then it's the integral part if we consider, then the value is the maximum value which may be for the vertex connectivity. So we can say vertex connectivity is less equals to the edge connectivity is equals to the 2e by n. Just for this explanation, we can say here that the maximum vertex connectivity in a graph G is the integral part of the number. So here the total number of vertices are 1, 2, 3, 4, 5 and 6. And the edges are 3, 4, 5, 6, 7, 8, 9. 9 edges are there. So as for the formula, 2 into e, that means 18. 18 divided by 6 means 3. So 3 is the number which is the maximum vertex connectivity is there. So maximum vertex connectivity may be the 3 or less than 3. In fact, the edge connectivity is also the maximum, it is 3 or less than 3. So for this one, if we just all these 3 theorems we combine, so according to that combination we can write the vertex connectivity is less equals to the edge connectivity is less equals to the 2e by n. So now for application of this cut set and cut vertex, I am giving you one situation. Suppose we are given in stations that are to be connected by means of E-lines. This line may be the telephone line, maybe the bridge, maybe the tunnel, maybe the highway, anything. So the question is, what is the best way of connecting these cities or these stations? So for example, let us consider there are total 8 vertices and the 16 edges. Vertices means the places or the stations to connect, and 16 edges means these are the number of tunnels or the lines which should be set up between these 8 nodes. So what should be the best possible connectivity? So we can connect this in this 8 vertices and the 16 edges as per this graph or this graph or this graph. Now the question is, what is the best way of connecting? The best we mean that the network should be as vulnerable to destruction of individual stations and individual lines as possible. That means if any particular station will be destroyed or more than that will be destroyed, but still the connectivity remains or the connectivity sustains. So if we want to set up our network in such a manner, then we should find out or we should draw the best possible graph where the vertex connectivity and the edge connectivity is maximum. That means the maximum connectivity value we should find out. If we connect according to this one, then the vertex connectivity 1. If we destroy this station, then the complete destruction will be there. This one is the another way of drawing the graph with the 8 number of vertices and the 16 number of edges. If we just inspect, then we will find out its vertex connectivity is 3. So this is definitely the stronger than this network, but not as much stronger. Now if we draw this one, here the vertex connectivity is 4 and that is the maximum vertex connectivity because total number of edge is 16 and vertex is 8. So 2e by n means it has to be 4. So not more than 4 vertex connectivity can be possible by using 8 vertices and the 16 edges. So if we draw the network in this way, then it is the best way of set up the network and it have the chance to sustain the as long as possible. In this video lecture, we are going to know about articulation point and bi-connected components. So what is articulation point? That already we discussed in our previous video. But in this video, we again discussing the articulation point in terms of induced subgraph. So previously we learned what is induced subgraph. Now it is the cut vertex or the articulation point. A vertex V in a graph G is called a cut vertex or articulation point of G if the induced subgraph G minus V has more components than G. So what it says, a vertex V in a graph G is called a cut vertex or articulation point of G if the induced subgraph G minus V has more components than G. So how to explain this one in terms of the induced subgraph? Let us see with an example. So in this example, we will have this graph. In this graph, initially we just identify the vertices by removal of which we may found the more components than the given graph. If we choose the vertex, this one, this 8 number vertex, then initially we consider this one vertex. Now we are going to find out the induced subgraph of this given graph. How to find out the induced subgraph? If we delete this particular vertex,
then deletion of this vertex will also delete the edges which are incidenting to this one. After deletion of this one, the remaining graph is the induced subgraph of the given graph. So if we remove this particular vertex, then after removal of this one, these edges will be gone, so that we will find out this yellow colored graph, and this portion of the graph will remaining. So the remaining portion, we say this is the induced subgraph. Now after getting this induced subgraph, we should count that how many components are there in this graph. So here the number of component is 1, this is for 2, second component, and this is the 3. So there are total 3 components in this induced subgraph. So in the given graph there are only 1 component, that means it is connected, that's why this is the single component graph. But after removal of this vertex, we will find out the subgraph which have 3 components. That means we will find out that the number of components will increase by deletion of 1 vertex in the given graph. So we can say that this particular point is the articulation point. So if by removal of only 1 vertex from the given graph, if it will increase the number of components in the induced subgraph, then it will called the articulation point. So here the vertex 8 is the articulation point for this particular graph, because after deletion of this one, we will find out the induced subgraph where we have total 3 components, which is 2 more than the original graph. So that this is our articulation point. Instead of the vertex 8, if we remove the vertex 7, then also we will find out that the induced subgraph contains this portion and this vertex, the isolated vertex. So this one will another component. So if we remove the vertex 7, then also we will find out in the induced subgraph the 2 components, which is 1 more than the given graph. So 7, this vertex is also one of the articulation point for the given graph. So this is the articulation point we can find out by using the induced subgraph technique. So now it is the connected graph. All of us know what is the connected graph. So a graph is said to be connected if and only if there must be a path from U to V, where U and V both are the vertices belongs to the vertex set of G. So suppose this one is the given graph. Here whatever be the 2 vertex we may consider, we will find out there exists at least one path between them. So that this is called the connected graph. So from the connected graph, we will find out that the connected component. So what is connected component? A maximal connected subgraph is known as the connected component. What it say? A maximal connected subgraph is known as the connected component. Here 2 words are very important. One is the maximal, another one is the connected. So the connected means there must be a path exist between any 2 pair of vertices in the given subgraph. First of all, any graph is given. From here we should find out the subgraph, and in this subgraph it should be whatever the subgraph we consider, that subgraph should be connected. So connected means that there must be a path exist between any 2 pair of vertices in the subgraph. And maximal means the graph G contains no other subgraph where all the vertices are connected. So what does it mean? Suppose this one is the given graph and we should consider one more part of this graph. So this one is a given graph where the 2 components are given. So now each individual components are the connected components. So each individual component means we can consider this one particularly as a subgraph and this one particularly as another subgraph. So both are the connected component because in between any 2 vertices of each of the subgraphs there exists a path. And one more thing, that is it is maximally connected. Maximally connected means there does not exist any subgraph which is, we can say this subgraph is the proper subgraph of that particular graph. So this one is the connected component. So any graph is given. If there are more than one components are given, then each component is the connected component, because in the each component there exist paths between any two vertices. Now, in a given graph, how to find out that connected component? So for that, we have two algorithms. Both the algorithms are known to us, and the name of these two algorithms are BFS and DFS. Yes, it is the breadth first search and the depth first search, which already we have the separate videos. But BFS and DFS are meant to find out the spanning trees. So yes, it is very obvious that the spanning tree means it is a tree, or it is a subgraph which connects all the vertices of the given graph. So the same process to find out in a given graph that there are connected components exist or not. The same algorithm, same way we just follow and find out that the individual components are connected or not. They are connected means we will find out the spanning trees for this all individual connected components. So accordingly, we will find out the connected components if exist by using BFS and DFS algorithms. So after knowing this connected graph and the connected component, now it is the bi-connected graph. That one is very important. So what is bi-connected graph? A graph G is said to be bi-connected if and only if it contains no articulation point. So we know what is articulation point. A graph is given. If we will find out on that particular graph no articulation point exists, then the graph is called the bi-connected graph. Actually, what happens? A bi-connected here graph means here no articulation point. No articulation point means there does not exist one vertex by deletion of which we will find out that the graph becomes disconnected. That means in between any two vertex there exists more than one path. In between any two vertex there definitely exists more than one path. If in between any two vertex there exists one and only one path, then definitely we will find out the articulation point, because by removal of a particular vertex we can separate these two areas. But if the graph is bi-connected means there are definitely two individual paths from in between any two vertex. So if we consider this one as a graph, then we may consider any vertex. Suppose the vertex 3 and suppose the vertex 2 we consider. So then this is connected by this edge. Again, this one is another path by which we can connect these 2 and 3 vertex. So that it is a bi-connected graph. And here no articulation points are given, because removal of any one of these vertices, it will not disconnected. So this is our bi-connected graph. Now it is a bi-connected component. So what is bi-connected component? A maximal bi-connected subgraph of G is known as bi-connected component. We know what is maximal. Maximal means there does not exist no proper subgraph, which is the no subgraph which is for which this one is the proper subgraph. So now bi-connected component is a maximal bi-connected subgraph of G is known as bi-connected component. So here you should understand that what it means. So any graph is given from there. Suppose this one is a graph. In this graph from here this vertex is the articulation point. So depending upon that we can separate the given graph into two blocks. So this individual block is the bi-connected graph. So if we consider this one as a subgraph, that is 1, 4, 5, using these vertices and these edges, if we create a subgraph, and 1, 3, 2, using this one we create another subgraph, then we will find out that each subgraph is a bi-connected graph. So these are the two components even, because depending upon this vertex it will separate it. So that these are the bi-connected components, because individually this graph is bi-connected, and these are the components according to this articulation point for this graph.
One thing you should remember here, for the biconnected component, it is always happens that no edges should be common among the biconnected components, but edges should be common, and that edges should be the articulation points, which are the common vertices. So if one is the articulation point, then these two blocks we can separate it. Now this one is common, this one vertex is common to this block as well as this one. So this component and this component both share the vertex 1, but no edges are common to them. So that in biconnected component, whatever be the different blocks we can find out, these all are individually the biconnected component, and you just remember that each component is a biconnected graph. And biconnected components never have the common edges, but they may have the common vertices, and that vertices definitely be the articulation point for the given graph G. One more example if we consider, then this one is suppose the graph. Here at first we identify which are the articulation points. So this one and this one, these are the articulation point. So depending upon that, we can separate the graph in this way, the blocks in these blocks. So just according to this one, this is the first block, then second, third, then fourth, fifth and sixth. So accordingly we just subdivide it. Now look, no edges are common to any of these blocks, but the vertices here, the 5, this one is the articulation point and this is common to these 3. This one is common to this one even. 8, this one is the articulation point, so that it is again repeated in the individual components. 9 is again repeated in the individual components. So depending upon the articulation point, we can separate a graph into the subgraphs, and those subgraphs are not containing any articulation point. So these are the biconnected components. So in this way we can find out the biconnected component. So just let me tell you the step to find out the biconnected component. At first, whatever be the given graph is there, from there find out the articulation point. Depending upon the articulation point, we should separate the graphs into the separate blocks, which blocks are individually the biconnected graph. So accordingly we can find out the biconnected components. So these are all the biconnected components for this given graph. In this video, we are going to learn about the different type of subgraphs. Among those subgraphs, we specially emphasized on spanning subgraph and induced subgraph. But before that, let us again just go through that what is the subgraph. So a subgraph B is a subgraph of a graph G if B of H, that is the vertex set of H, is the subset of the vertex set of G, and the edge set of H is the subset of edge set of G. That is, if H is a subgraph of G, then it will imply H is the subgraph of G. Therefore, we say H is contained in G or G contains in H. With an example, if we emphasize on the subgraph, then let us do with this example. Let this one is a given graph. From this graph, if we want to find out the different subgraphs, then the subgraphs may be these all, this one or this one or this one or these all. So what is the concept to take the subgraph? From this given graph, we may delete any vertex, any edge. After deletion of that, the remaining graph is the subgraph of the given graph. For this one, we have deleted the vertex 5 from the given graph. So vertex deletion means its incidenting edges should be deleted, because without a vertex, no edge can be survived. So if we delete this vertex 5, then this edge definitely be deleted. Accordingly, we will find out this graph, and this is called the subgraph of the given graph G. Next, if we consider this one, here 1, 2 and 4. So the vertex 3 and 5 should be deleted. So 3 means these two edges and this vertex, and the 5 means this vertex and this edge should be deleted. After deleting all those, we will find out this graph. So this one is a subgraph of this one. Similarly, we can delete 1, 2, 3, these all 3 vertices and the corresponding edges. So the remaining portion is this one. So this one is a subgraph. Again, if we delete the vertex 2 and 5, then by deletion of 2 and 5, these 3 edges should be deleted and this edge be deleted, then the remaining graph is this one. So this one is a subgraph of the given graph. Similarly, this one is also a subgraph. If we delete this edge and these 2 edges only, then these vertices, all the vertices are here and only this edge and these 2 edges are missing. So this one is also a subgraph. Not only that, if we delete all the edges and keep all the vertices, then this one even a subgraph. So subgraph means you may delete any vertex, any edge from the given graph, then the remaining graph is your subgraph. Here 2 type of subgraph for we are discussing. So these 2 important type of subgraphs are edge disjoint subgraph and the vertex disjoint subgraph. Edge disjoint subgraph means from a given graph, if we take 2 subgraphs and those 2 subgraphs have no common edge, then this is called the edge disjoint subgraph. Similarly, the vertex disjoint subgraph for if we take any 2 subgraph from the given graph and among these 2 subgraphs no vertices are common, then these are called the vertex disjoint subgraph. For example, if this one is the given graph, so from here one of the subgraph we consider by removing all those edges and another subgraph we considering by considering only these edges and removing the outer edges. So in these 2 subgraphs, if we find out, then no edges are common. So these are called the edge disjoint subgraph. Similarly, for the vertex disjoint subgraph, if from this graph we consider the subgraph containing the vertex 2, 3 and 4 and these 3 edges corresponding, this is the one subgraph. And another subgraph for if we consider the subgraph which contains the vertices 1, 5 and 6 and these edges, then this is another subgraph called H2 suppose. First one is H1 and then it is H2. If we take the intersection of these 2, then we will find out that no vertices are common over there. So that this is called the vertex disjoint subgraph. Now it is the spanning subgraph, which is the very important subgraph. So what is spanning subgraph? A spanning subgraph is a subgraph obtained only by edge deletion. That is, the vertex set of the subgraph is the entire vertex set of the original graph G. So how to get the spanning subgraph? Suppose any graph is given this one. From this given graph, if we delete any edge or any number of edge, either 1 edge, 2 edge or all the edges even, but no vertex can be deleted. After deletion of any edges, the remaining graph which is there, that one is called the spanning subgraph. So it should be ensured that in a spanning subgraph means in original graph and in the subgraph both have the same number of vertices. So for example, this one is a graph and if we delete this one, then we will find out this one. All the vertices are there, so this is the spanning subgraph. Likewise, this one is also one of the spanning subgraph. This one is a spanning subgraph. This one or this one. All are the spanning subgraphs. Remember, here this one and this one both are the same graph. That means any graph itself is its spanning subgraph. So this is the spanning subgraph. Next, it is the induced subgraph or the vertex induced subgraph. So what do you mean by the induced subgraph? A subgraph obtained only by vertex deletion is called an induced subgraph. So in a vertex induced subgraph, we have to remove at least one vertex from the given graph. And the vertex deletion means automatically the incidenting edges also be deleted. So if this one is the given graph and if we delete suppose the vertex 1, then its corresponding edges also be deleted and this one is the remaining graph. So this one is called the vertex induced subgraph. Likewise, if we delete the vertex 5, then these edges will be gone. So the remaining portion is the subgraph and this is called the induced subgraph. Again, if we remove the vertex 5 and 4 both, then this one is the remaining portion and this is called the induced subgraph. Likewise, if we remove the vertex 1, 3 and 4, then the remaining portion is 2 and 5 and this edge is there. So this one is the induced subgraph. So in the induced subgraph, it should be remembered that number of vertices in induced subgraph must be less than the number of vertex in G, and deletion of vertex implies deletion of incidenting edges also. So these two are the important thing over here. So in this way we can find out the induced subgraph. So in this video we just sum up with that one, but few more subgraphs are there, and the very important subgraphs are these, so such as the clique and all. So that we will discuss on our next video lecture. So have a nice day. Thank you all.